Imagine if the universe had two different rulebooks, one for big things and one for tiny things. Today, we will explore quantum gravity, a quest to combine these rules into one grand theory. We'll first meet two famous theories, then see why they clash, and finally, discover what happens at the universe's smallest scale. First, let's talk about general relativity, Albert Einstein's amazing theory of gravity. It says gravity isn't a force pulling objects. Instead, massive objects bend the fabric of spacetime. Think of spacetime as a giant, flexible trampoline. Heavy balls make dips, and lighter balls roll into those dips. So, planets orbit the sun because the sun's mass curves spacetime around it. Spacetime is the four-dimensional stage where all events in the universe unfold. Next, we have quantum mechanics, the theory that describes the super tiny world of atoms and subatomic particles. In this world, particles behave like waves and can be in many places at once, full of uncertainty. Energy and matter aren't smooth, they come in tiny, discrete packets called quanta. Now, here's the big challenge. These two powerful theories don't play well together. General relativity works perfectly for large-scale objects like stars and galaxies. Describing gravity as smooth, quantum mechanics excels at the smallest scales, where everything is lumpy and unpredictable. The problem arises when we try to describe gravity at the quantum level, where spacetime might not be smooth anymore. Imagine spacetime as a calm ocean from far away, like general relativity describes it. As you zoom in, you see individual water molecules moving randomly. This is like quantum mechanics' view. How can we describe a smooth ocean made of individual, chaotic molecules? That is the core conflict. This leads us to the Planck length, the absolute smallest possible distance in the universe. At this incredibly tiny scale, spacetime itself might start to look fuzzy and bubbly, not smooth. A quantum theory of gravity would describe what happens to spacetime at this ultimate smallness. The search for such a theory is often called the quest for a theory of everything. This theory would unify all fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces. To understand the challenge, consider our ocean analogy. From a distance, a ship smoothly sails the sea. But how would a ship move if the water itself was a boiling, uncertain foam of tiny quantum particles? That's the puzzle quantum gravity tries to solve. How gravity works when spacetime itself behaves quantum mechanically. Reflect on the immense difference between a planet orbiting the sun and the bubbling chaos at the Planck length. It highlights why it's so difficult to create a single theory that explains both extremes. We've explored Einstein's general relativity, which explains gravity through spacetime curvature. We also looked at quantum mechanics, describing the unpredictable, discrete world of tiny particles. The challenge is unifying these views, especially at the super small Planck length, where spacetime might be granular. Quantum gravity aims to bridge this gap, offering a single set of rules for the entire universe. This ambitious search for a theory of everything continues to push the boundaries of human knowledge. It invites us to imagine a universe where all its mysteries are finally understood through one grand, beautiful idea. Generate your own educational videos for free at eduvids.vercel.app.